Okay, can everybody hear me? Excellent. So first off, I appreciate everybody being patient with us getting this together, with me getting my part together here. And I think this is going to work for us using this kind of format, but we're trying this out and I'm willing to take suggestions and modify how we do this as this goes on. So I initially created this room so that when everybody comes in, they're coming in muted. They can request to go unmute and we can work with it that way and see if that's a better format. I also have a chat window open so I can monitor that as we're going along, and if it is if I'm not seeing your hand raised or anything like that, then just say something on chat and I'll be looking for that. I've actually got the answer to your question there in the chat room is that yes, you can go ahead and do screen record. I've also turned on the recording session for Zoom itself, so we'll see how well that works, and I can share that as needed. Okay, I guess we'll go ahead and get started then. It is 5:30 now. Um, Seems weird not having any vocal feedback, so having everybody muted right now is something I'm not sure that's good or bad. I'm sure it'll get pretty cluttered if I just let everybody go live here. So we'll see. We'll see how this works. Okay, so I'm probably not going to go a full lecture today because mostly what I would like to do is see how this works for everybody and what we need to do as far as making modifications to this so it's best for everybody. Interesting. Okay, so let's go and change the screen share to there. Okay, I believe this is where we left off. We had gone through and talked about relocation bits, and we looked at how we were going to use a new type of format where we were using the names, right, for the symbols instead of the actual address or the offset number, because we're going to be working with multiple control sections. And working with multiple control sections means that at compile time, we are not going to know what the addresses are of the other symbols in the other control sections until it's actually loaded into memory. So doing it this way allows us to be able to eventually construct some data structure that the linker can then use, and the loader can use rather, to be able to do modifications to each control section as each other control section is uploaded. So that's what that discussion was about, as you probably recall. And then we talked about how that changed in the object code itself, which is what this example here was. So I believe that should get everybody up to speed now, right? Okay, so the next thing to address then will be talking about how the external reference and the external defines are going to work when we're going across control sections. And the way that's going to happen is we're going to use these symbol names, and we're going to have to create a different structure that the loader can use to be able to address those cross references. Okay, so looking at the example code in figures 3.8 and 3.9, what I have done in these next few slides here is I've done some color coding so that it kind of pops out what each of these different tables are trying to show and share with you. Specifically, if you're looking at the stuff that's highlighted in blue, that is what is unique to this particular control section. The stuff that are highlighted in red are those things that are similar, but they exist in other control sections. And we're going to look at those that are in the reds and the blues in these next 3 slides here. The items in black, they don't change. They're going to be unchanged across each of these different control sections. Okay, so let's take a look at this one then. Okay, we can see here that just going down the left column, where the prog A symbol name is, as you recall, that's where we are defining symbols. So you can see here in highlighted in blue are list A and end A. Those are the only 2 symbols that we are creating that are new to this control section here. And you can see that we also chose to use the EQU assembler directive with the star. And as you recall, that would tell the assembler that when the assembler is generating the machine instruction for these addresses here, that it would determine what the address or the value in this case is for list A, and then it would provide that to that symbol. So we don't have to calculate it, and you don't have to calculate it. It's the assembler that's going to calculate that for us and then just populate the symbol table with the right value. However, that's not all of what we're doing here, because up at the top you'll see that we decided to use an external define. External define are those assembler directives that we're going to use to say, hey, these symbols here, in this case list A and end A, are symbols that we want to create in this control section, but we want to make them available to other control sections outside of this one. Likewise, when we have symbols from other control sections that we want to use in this control section, we will use the external reference, EXTREF, assembler directive, to say, hey, these symbols, you can see list B in B and list C in C are listed right there, are symbols that we want to use, but they're not defined in this control section. They're defined and created in other control sections. Now, the reason why we need to do that, as you might recall when you're going back and looking back at how we assembled each one of these source code files in the past, is that for every symbol that we use, and that would be used in this column here where you see list A and list B in blue and red, those have to be created, defined somewhere. And that's where we went to that second column and found that we created list A and end A in this particular control section, but we never created list B and end B or list C and end C. So that would create an error on the part of the assembler when it's trying to generate code for this control section if it did not know how to resolve those symbol names and say, hey, they were created here and they have these values and they have some type. Remember, we have different types that we have for them as well. So by using the assembler directive external reference, what we're doing is we're telling the assembler, says, hey, just pretend that they've been properly defined, but they belong outside of this control section, and we'll have to figure out their values some other way. That's really what it's saying. Hopefully that makes sense. So if it's not, of course, you can always open up something in chat or raise a hand. And let's see. Got that. Sure, I can repeat the difference between external def and external ref. The external define, or the external def, means externally define. Yeah, raise your hand thing. I'm still looking for that window so I can see that. I just saw that I've got the chat room open here and I'm still trying to find the place for the audio control for the participants. Let me see where that is. Come on. Oh, there we go. Yeah, so I just noticed too, one of the challenges I'm going to have with the raise hand is that not everybody fits on the screen. So if you're raising your hand, I don't know if it pops you up to the list. Somebody want to raise your hand now? That does pop you to the top of the list. Oh, great. Okay. Okay. I think I got it now. Sorry about that. Appreciate your patience. Do this way. That should work. Okay. Now I think I got a better layout here on my screen. Okay, so the last question was, could I go over extdef and extref again? So extdef is externally defined. Okay, those are symbols that we create in this control section that we want to make available to other control sections. extref, externally referenced, are those symbols that are created in other control sections, but we want to use in this control section. Okay, other questions on this slide? All right, we'll go on then. Okay, so on the second one, this is very similar to the one we just looked at. Here we have two symbols, list B and end B, that we created in this control section. And then you can see in this, let me try something here. I want to make sure you can see my pointer. Yes, you can see my pointer here. So in this column here, you can see where we are using the different symbols, of course, and not just the list B and the end B that we created in this control section, but also these other four symbols that we're using from other control sections, list A, end A, list C, and end C, that we're using in various places. So one of the things that we also have to be aware of is that when we're using these symbols in this column here as an operand, as a value, or as an expression, we need to worry about whether or not they're going to be generating relative or absolute values, just like we were before. So that means, of course, that those rules about addition and subtraction of relative with a relative, relative with an absolute, absolute with an absolute, those are still in play. And we're also going to have to be aware that the starting address for any of these symbols is going to be different depending upon where it actually gets loaded, unless it's just a relative term, in which case that doesn't matter. So these first two examples up here are pretty straightforward, list A and list B, right? They're just some symbol that is created in this, excuse me, another control section, a symbol created in this control section that we're also using it as an expression, and it's going to generate a value. Yes.
What would control sections look like on object code? Is there a way to differentiate?
We haven't looked at that yet, but we will.
Okay.
Okay. All right, so then we also have the things like the immediate value of end A. That of course is going to apply only to this one symbol, right? That doesn't mean immediate value and then a parenthetical expression, because we don't have that mechanism, and so therefore it would only apply to that one symbol. Okay, well, some other novel things are down here. Okay, so speaking of parenthetical expressions, we can come down here next to the last line here, where we did introduce the use of parentheses in operations, which is forcing the whole evaluation precedence of order, what we refer to as precedence. Okay, so what that says is that pairwise, whenever we see an arithmetic operator, we always operate pairwise, and we're always going in this particular machine language from left to right. So this left to right grammar says, okay, our first symbol is end A, we have an operator, we have a symbol list A. So we have a pair of symbols and a single operator, we go ahead and evaluate that. So we go ahead and do that. And then now that's reduced to a single symbol and an operator. And now we have the parentheses, which means we need to go inside the parentheses, evaluate these two symbols with their operator, and then we take that result back out against and evaluate it against there. Now, since this example here, end B minus list B, are both in this control section, we can calculate that at assembly time. So we'll go ahead and do that. We'll have the assembler calculate that value and then actually generate code with those numbers. Well, let's see what that is. End B, okay, is going to have an address 70, and list B is going to have an address 60. So the difference is now 10. But we have to remember that this column here is base 16, and that this column here is in base 10. So when we take 10 in base 16 and convert it back to hex, that's of course 16, which is then where we got this number here. Okay, another one I think to be easy to see here will be list B minus list A. And this is probably going to be helpful to understand that previous question, or it was 2 questions ago, where we know what the value of list B is. By the way, if I'm over-modulating or under-modulating, you can let me know that here, because I have a fairly new audio setup, so I'm working with adjusting that correctly. But list B, we know at assembly time as well. Okay, so 7C in base 16 is going to get calculated to 60. List A, what this points out here is that we're going to have to, when we go to load this into memory, this particular assembled code into memory, we're going to have to take list A and we're going to have to subtract that from this address. So we're going to have to worry about how that's going to be done. Okay, so we haven't talked about that, but I'm just kind of giving you a heads up about some novel things that we're looking at here, and some things to be thinking about when you're doing your readings, and we'll be talking about next lecture here. Oops, I did pop forward through control section C. There we go. So now looking at control section C, our prog C, we'll see that it's similar because we just want to change. We want this to be very similar to all three control sections, but unique so that we can see how this works across control sections. So you can see that we've created two symbols here, list C and NC, and we're making those available to the other control sections. Now it's probably worth noting at this time, we've said it, but it's probably worth noting at this time that when we do this external define here, that's making that available to the other control sections. But if for some reason we had skipped and did not include something like the symbol NC, then that means when the other control sections did their external reference control C to NC rather, but if it hadn't been declared with this externally defined here, then it wouldn't be able to use it. It would not see that as available, and therefore that would create a load time error, a runtime error actually, as the loader was trying to load this up in memory because it was trying to reference a symbol that it knew nothing about because an external define or an xdef had never been used. Okay, so that's important to prevent those kind of runtime errors, that you do that cross check to make sure that everywhere you've done an xref, you've done an xdef to create it and make it available. That's okay if you've externally defined symbols that you never used, although good clean code says no, you don't want code that's unused out there, but that's just cleanup stuff. For kind of understanding what's needed is what we're really focused on here, and making sure we get that part right. So for every external ref, we want to make sure that xdef has been created for it, and then we'll worry about cleanup later on. Does that make sense? Okay. All right, so that's this example here with the 3 source code files, and talking about how we can use these symbols that are across control sections. Does anybody have any questions about how that works, or you think you got it? Okay, so I don't see any hands going up, don't see anything in chat. So we will go ahead and go into the next discussion, which will be taking a look then at the source code that we need to generate, not the source code, the assembled code that we need to generate to implement these control sections. Okay, so the header record, there's no change there. It's going to look just like it saw before. Forgot I can do this. This might be easier to see. So the define records, okay, are new, as are the refer records. So just like we saw up here, we were using this external define and this external reference as new assembler directives for us to be able to create these symbols and use these symbols. So for code generation then, we are going to need to provide that to the loader itself. And so we're going to do that by using these define records and refer records for external define and external reference. External define will just simply list the symbols that we created in this control section here that are making available, defining those for other control sections to use. And we'll make on these refer records a list of those symbols that are using symbols that were created and defined in other control sections. So here we are in prog A, right? So prog A, we created list A and end A. So what we're going to do then is we're also going to use or refer to symbols list B and NB and symbols list C and NC. Then we generate the text records. No change there, just like we had before. And now for the modification records, what we're going to do is we're going to generate for every address that we used either an absolute value symbol like prog A. Prog A was the address that the program was loaded into. Go back here, right? That was the very first instruction. We set it at 0, but that means the loader can load it. So at some point here, when it gets loaded into main memory, we're going to need to take any address that used prog A. In this case here, we used prog A down here when we were creating this end A minus list A. I'm going to say why we need that here in just a minute, but that's what we're referring to. So coming back down here, so address 5A, we're going to come back and visit that and say we need to add the location of prog A to that particular address. So let's go back to some more obvious ones. Let's say at address 24 in prog A, address 24, which is where we have this list B symbol, and then we're going to add 4 to it. Well, it was an LDT instruction. We went ahead and assembled that. It was plus format, so it's a format 4. So we went ahead and assembled that, and we added 4 because that's what we're doing here is plus 4. So we can do that right there at assembly time, but we don't have list B. So when we go to load this in memory, we need to find the value of list B and add that to this address. Well, not 23. We want to skip over that first byte because that's the machine instruction like we saw before. So here at 24, and for the next 5 nibbles, or for a total of 5 nibbles, here's where you can see we will now add that list B to that address. That make sense? Okay, let's come down then to address 54. So 54, we had an end A, which is 54, minus a list A, which is 40, which we took a look at that earlier. We had the 14. I see we have a question. Do you need a modification record every time you use a symbol? The answer is anytime we use a symbol that's outside of this control section where we don't know its value at assembly time. So we are going to have to then modify it at load time, which is the only time we can find the value in that other control section. For our own symbols inside, none of the rules change from before. That is, if you have a value that you can calculate, the assembler rather can calculate, it's generated at the spot. If it turns out that it's a relative value, you're good. But if it's an absolute value, then at load time, we still need a modification record. So in this case here at line 54, we did the end A minus list A, 54 minus 40, there's the 14, but we don't know the value of list C at assembly time. So that's where here we will then take 54, and now we want to, since it's a value, it's not an instruction, we want to take the value of list C and add that to whatever is at address 54. Okay, and we'll just continue doing that for every one of these symbols, just like I was answering that prior question from Andrew, was that every time we have a symbol outside of our control section, we're going to have to go and grab that value from a modification record, which means at load time, when this gets loaded up, we can resolve it then. And then whatever we've done already, like calculating this 3F list A minus 1, we can do that and at assembly time. And so therefore we, at address 5A, only need in A minus list C. Except, let's come back here. Too far. Except this is the one that's really interesting, because list A, right, is a relative value 40 from the starting of this control section. Its value is 0. This is not an absolute value, direct value. This is going to be relative from wherever it gets loaded. So the actual value of list A is going to be whatever relative value in here plus wherever it gets loaded. The problem is we don't say that here anywhere. So this turns out to be an absolute value at 5A. We have NC, which is a plus. That's probably worth mentioning too. That's a plus NC. It's a minus list C. And now let's go see what we're doing at 5A here. So 5A here, here's the plus NC at 5A. Here's the minus list C at 5A. And then here's the plus prog A. So what we're doing then is we're taking the actual load address for prog A, adding that to there we go, adding that to this value of list C minus 1, which was 3F, to get the actual value. And I see in the chat session somebody was helping out there. Fantastic. Yes. Okay, and so we'll do that for every one of those symbols in the control section. This is control section prog A, and when we go to control section prog B, it's going to be similar but different, right? Because it has a different arrangement of symbols that it's doing work on. And so we'll just apply the same logic with it. Okay, list A on line 36, we're going to need to be able to grab that. This is prog A, prog B. We're going to need to grab that at address 37 and add that to that location. Recognizing that all of this up here is the same, right? We're still creating the header record, the define record unique to control section prog B, and the refer record that's unique to control section prog B. Those are still unique. They're similar, but they're unique to this control section. But then determining all of our modification records that we need is just simply going to be going down all of these symbols that we use here in the operand side and determining if we need to pull those in or not. Any one that is used as an expression or used outside that needs to be pulled into here, yes, we'll have to get all of those. In the case of like an expression within B minus list B, we did that at assembly time, but we still need to take the rest of this expression, which is plus end A minus list A, and then subtracting that from here. Then when we look at control section prog C, we see something similar. We have the control section prog C, it has its xdef and so on. We went through that, but for its code that we need to generate, It'll have its unique defined record for list C and NC, its refer record for list A, end A, list B, NB, and then we will need to go down and generate unique modification records for each symbol outside of the control section, as well as every absolute or direct value for symbols inside of this control section in order to get them offset to the load address. So any questions on the xdef, xref, and the define and refers and their corresponding modification records? That was the only example that I had come prepared for lecture, but yes, I can gin some up for the Wednesday lecture. Okay, sounds like everybody's on board with that. Then the next thing we can do is we can take a look at then another example in another way here. So what we're going to do is we're going to take prog A, prog B, prog C, and give them some fictional load addresses. Okay, I'm not saying there'll be this value every time, just for sake of being able to run through some numbers. Let's say that they get loaded up at these addresses here. Okay, so what we're going to do then is we're going to see if we can calculate some actual values for some symbols. Let's look at the next slide and we'll come back to here. Okay, going back to our memory map, right? And we said, okay, we want to take an example of using address 4000 for the load address for prog A, which is what we're saying here, the length of 63. And then we're going to say we're going to take prog B and we're going to set its load address to be right after prog A. So it would then get loaded at 4063 with a length of 7F. And so that's what you see here, 4060, 1, and 2. So 4063 would then be the first byte for control section prog B. Okay, and then it has a length of 7F, which takes us out to there. So the starting address then for prog C, if it was loaded consecutively, would be 40 echo 2. And it has a length of 51. So 40 echo 0 is here, echo 1 is here, so echo 2 would be that byte right there. And then prog C would be loaded up to 4031, 32, 33. Okay, so these three control sections happen to get loaded up consecutively. Note they don't have to be. The loader could choose to load them into different places. Each one has a unique starting address and a length. And that's all that the loader really needs to know to be able to determine addresses and values for these different symbols and their modification records, and then be able to do the correct arithmetic to be able to change those values that have those modification records. But to do that, you have to know how to do that. And so what we're going to do is we're going to take a look at these examples here. What are the calculated addresses for list A, list B, and list C? So if we go back to prog A, list A was at address 40. List B at 60 in its control section, and list C 30 in its control section. So 40, 60, and 30. So what we're going to need to do then for list A, list B, and C is that we need to take the load address for prog A, and we're going to need to add 40 to it, which is 4040. For list B, we're going to need to take the starting address of prog B and add 60 to it, which will come out to 40C3. And for list C, we'll need to take the starting address of prog C and add 30 to it, which comes to 4112. Now, I don't want to talk about that just yet. Okay, so these are just three. We're going to need to do this for any absolute address. The relative addresses, of course, don't matter, but these were absolute addresses. So what that's doing then is defining this memory map, exact locations where list A, list B, and list C are located, and this is how we can get to those addresses specifically. Now, the other thing to look at will be an example with ref4. So ref4 in prog A, this line here, okay, has this calculation here where we took end A minus list A. End A minus list A, which yielded a relative or a direct address value. Direct, why? Excellent. Now list C was pretty obvious, right? We took list C and we said, okay, we're going to need to find its value. Well, we calculated that up here, 4112, right? And so we would take just this expression here alone, right? We would take the 4112, we would add the difference of these two. Stay with me for a minute. And of course, that would just come out to 4126. Now, let's go take a look here and see why we need to think about that thoroughly before we just accept that. Okay, so ref4, okay, we said it had a value of 14 because we calculated that difference at assembly time, because we said that's a delta value there that can be calculated by the assembler. We said, here's the difference, it's 14. Put that in the text record. Okay, but the next thing we did is we took and subtracted list C from it. Well, list C has to go to where prog C was loaded, and we need to start with the starting address of prog C, which we then need to take and add that offset value of 30 to, which is how we got the 40E2 by doing that addition. And now what we do is take 4112 and add the 14 to it to come up with 4126. So now that you've seen that, do you think that subtracting these, ref4, do you think that subtracting these yields an absolute or a relative value? Value from a direct address of 5406 minus 30. Where would you get the 5406 from? Yes, that's correct. So that's why this illustration I think is also helpful to understand that even though this is the memory map, we were talking about the symbols inside of it. And so having calculated that delta of 14 here, which it was two absolute values that we were then subtracting one from the other, which yielded a relative value, which is where we got the 14 from. And then the reference to list C, yes, because that's the modification record. So the reference to list C then was, it starts at prog C, but it was offset 30 from the starting address of prog C, which is where we got the 40ZE2 plus 30 to get 4112 added to the 14. That's how we got the 4126. Okay? So the last thing I wanted to cover tonight then will be taking a look at this new data structure that we're going to need to help the loader be able to do this resolve these addresses for these modification records at runtime across control sections. Okay, so the linker section of the assembler was generating those modification records based upon those rules we talked about. So the assembler ran, it generated all of those xdef, xref, which generated, I'm sorry, the programmer generated the xdefs and xrefs. The assembler ran, which created the define and refer records. The assembler then generated those values. So what the linker did. So what the loader is going to do now is it needs to have a new data structure, and we're going to call it the ES tab for external symbol table. So this external symbol table is this data structure here, which will have the name of the control section, the symbol, and we'll do it by control section, list A and end A, list B and NB, list C and NC, and then their address or values. Now, in the case of the control section itself, we'll also record the length of the control section. So we can calculate those values at load time, because we'll know the starting address of prog A, prog B, and prog C at load time, but we don't know it at assembly time. So what's going to happen is, as the loader runs, it's going to look and see what control sections exist in this overall program. It's more than just one control section. In this case, we have a program that has 3 control sections, prog A, prog B, prog C. And so it's going to create entries in the control table, entries in the ES tab, the external symbol table, with the control section name and its length initially. It'll also know these symbols by control section because it's reading the external defines in each control section. So what it'll do is, as it's loading the first control section, prog A, it finds an address based upon the length that's needed. And it says address, in this example here, 4000 was available. So 4000 was available, length of 63. Then it can come through for those 2 external define symbols and say for list A, oh, that was offset by 40, end A was offset by 54. Well, now it has a starting address, so it can quickly calculate the 4040 and the 4054. Likewise, for control section prog C, it finds an address, and it just happened to be consecutive, so it was 4063 rather, with the length of 7F, and it does the same thing for list B, NB, list C, NC for prog C control sections, same thing. So what's going to happen is, dynamically, if the program is running and for some reason one or more control sections get swapped out of main memory, and then the next time this program gets to run again, maybe it got paused while it's waiting for some IO to complete or something, and once it completes that, it gets loaded back in. It could get loaded into a different address, or the whole program could go away, and when the program gets loaded again, it could get loaded at some address other than 4000. What's going to happen is, for whatever control section the loader is loading into memory or back into memory, it just updates the starting address of that control section. It has the length, so it knows how much memory to get and that there's memory available for it to get. It'll get that memory address, and then it'll update the values of list B and end B so that every time prog A is loaded, it can then update its values of list A and end A from this table. Or in this case, list B and end B from its table if prog A is reloaded, or if prog C is reloaded, it can then reference prog B's entries for list B and end B in order for it to be updated and use the correct values given the new load point for prog B. Okay, I don't want to go into the one pass, two pass discussion at this time. I think we will save that for Wednesday. Okay, do we have any additional questions? Hands, I see somebody, oh yes, so we got, we're going to limit participants next time. Okay, any other questions? Okay, likewise, any suggestions or recommendations? That midterm grades, yes. I was going to do that this weekend, but spent time doing this instead, as well as taking care of similar issues on my day job. So I unfortunately did not get to correct those, but I will be getting to that here by the end of the week. The stats of midterm one exam number one will be updated as well once I've finished reviewing them. And the TA is available. I don't have any updated hours from her yet. I'm talking with her about that. You can email her anytime, of course, and then we will get her to post her virtual hours and what that looks like here shortly. And the testing mechanisms will be different. I've been wanting to start taking a look at some of the online tools that we have available for some online testing, and it looks like they will support what I want to do, so this is an excellent time for that to happen. I will still be using prose style response questions as well as a few of the multiple choice type of questions. In some cases are fill in the answer blank questions, but we will be still doing prose style responses, and the tools support that, so I don't see too many differences there. Will the syllabus change at all? It will a little bit. The thing that I want to make sure we reflect is that the format for the exams is different, and the turn-ins will be a little bit different, but so I want to capture that, yes. Good choice. Good suggestion there, so I will take that into account with the fill in the blanks. Okay, other questions? The other thing I think I will do as well is I will go ahead and start a discussion board on Blackboard, and so that anytime between lectures there's some discussions or questions that you bring up, we can use that in conjunction with this. So I'll set that up here tonight, and we'll make sure that we keep the information flowing that way, because I don't want anybody to just sit there and wonder, and there's no sense to wait for the next lecture for a question and answers. So we'll do the discussion boards as well. Okay. So no more questions. I then will go ahead and close this off. I'll start up the discussion board, and we can see everybody there.